I think we're going to resume our, we're going to resume our discussion on, continue discussion on NPN. Let me phrase it again. Our discussion is, for now, is limited to NPN transistor, and it's operating in active mode. So everything we talk about is only valid in active mode. And there's a lot of confusion on this model that I'm trying to convey here, the exponential model. So when you're using exponential model, we're defining the BE junction with a diode. But the BE junction, remember the current is being split, right? So this is the only, this only accounts for the whole current. This only accounts for the electron current. So the emitter we're taking both, right? The emitter we're taking both the whole, the total whole current and electron current. So the current ratio between whole current and electron current is beta, right? We already know that. So IE versus IH is beta. So if you want to describe this BE junction, the current flowing through this with a diode, meaning that you have to adjust your diode parameters. So remember, if I'm using a diode, if I'm using an exponential model, diode, let's say if this is D1, so D1's IS is IS1. So the IS1 I'm referring to is the reverse bias saturation for D1. So the relationship between this diode's IS1 and the IS describing collector current will then be IS1 will be beta. That is why you get IS1 as IS beta. Okay? So IS1 is not the current going through the diode. IS is the device parameter describing D1. Okay? I shouldn't have to step. Okay? Good. So once there's another question we're going to address a little bit later. I don't want to confuse you with too much physics because it's somewhat complicated. But based on our understanding, typically you will, for a transistor, let me emphasize, let me try to convey this. So for a transistor, you typically look at two characteristics. One is how it turns on, and the other is how it delivered its output characteristic. So if you're looking at the first, is called the IC. IC, remember IC is typically my output terminal. So you want to look at IC VBE characteristic. So this is one of the ways to test this. Is if I give you a transistor, you want to test how well this transistor control its voltage. Its voltage control its current. The way to test this is that I would then measure under a fixed bias, under whatever collector bias, and then I'm ramping this input. So if you want to test your device, this one of the characteristics is to look at the turn on characteristic or control characteristic. This is basically you want to see how well it's being controlled. Okay, so we measure collector current. So what is being measured through the ammeter is the collector current. And then you ramp the input because the ramp input is VBE. So we ramp VBE and add a constant VCE, collector to emitter bias. So typically what you will observe will be something very close to a diode because this is simply a diode control. Remember, this is simply a diode. You just suck up the electron part. Okay? So this is just a diode current. Remember, I'm just taking up the part of the diode current. ignoring the whole current, just taking out, but the characteristic is the same. So what happens is that it will look very much like a diode, like this. Exponential increase. Right? So that's how we approach it with a VBE-on. You can use a VBE-on to describe it. Right? You use a constant voltage. So this red is the constant voltage model. Use a constant voltage model to refer to the exponential dependency. The other key characteristic, if I give you a diode or you make your own transistor, if you make your own transistor, other than the turn-on characteristic, the other characteristics would typically are very concerned or are key of delivering whether your devices actually work as an amplifier, especially when we're operating as an amplifier. Is that we're going to look at what we call the output characteristic. So how does one measure this? So if you build your own transistor or you buy one, what we do is that instead of I'm giving you a fixed bias, this will be a fixed VBE. And then what happens is that I'm still measuring collector current, but ramping output voltage. So I'm ramping VCE, given a fixed bias condition, fixed VBE. So you fix your control, but look at the output current characteristic. So this is called the IC VCE characteristic. So you look at IC, measure IC when ramping VCE. So we already know that if you look at this IC versus VCE, based on our previous analysis, we know that, let's say, this is my VBE. Let's say my VBE is 0.8 volt. So if I'm starting from VCC, so you always start from the boundary. We know that if I'm starting from very high voltage on the emitter, this junction will typically, you can guess, it will be in reverse. So when your collector voltage is at a higher voltage, it will be mostly in reverse. It will only become saturation when it suppresses down to lower than VBC. So this would then set your boundary. So you expect that this would then follow a fixed current, right? So this will be VBE1, this will be VBE2, this will be VBC3. So you're given a different amount of forward biasing condition, you then allow different amount of current flowing, which will be independent of VCE, but a constant current because it's voltage control current source. VBE control current source. So only VBE changes, the current changes in response to VBE rather than VCE. But then when it enters saturation, what do you expect? So this is, we know by definition, this is when BC in reverse. Why do I know that? It's because B minus C, this voltage minus this. So you have to higher than this to make sure that your BC is smaller than 0. So only in this region, this fulfilled BC junction in reverse. So we know that in this region, this is an active mode. So by definition, if my collector voltage, VCE voltage, is smaller than 0.8 volt, for example, that simply means that in this region, VBC start forward biasing, right, in this region. So this, by definition, it enters what we call saturation. So we're not going to talk about saturation yet because I want to go into I want to still continue on active mode on small signal model. But just to give you a sense, what do you expect? As I said, the analogy is that if I'm putting out perfume at the front, and you're supposed to create a suction in the back, so that will create a gradients, large gradients, so that I will have constant current flow, the best condition for current flowing through the base, right? So what if the other guy on the other side start pumping perfume? That would then, as I said, the reason why it's called saturation because your minority carrier will saturate the base. Saturate the base meaning that it will then decrease your profile, decrease your d and dx. So during saturation, what happens is that you will expect d and dx will increase, will decrease. Therefore, you no longer have a zero at the back. There's no longer suction. You're forward biasing as well. So both sides are creating large minority carrier inside the base and then reducing the gradients. Therefore, you expect IC to decrease, of course. So then what happens is that you assume that it will decay. But in most cases, the thing is that in saturation, you're assuming that it will decay well, but it will take a while. And we're going to explain that in a little bit. But what happened is that, so as I said, there's two definitions of saturation when we actually come to discussing. One is that it's actually forward biasing, but even though they're pumping a little bit, because the exponential factor in this term, therefore, even though it's pumping, you don't actually see it. So it does not create too much significant difference in your gradients. Only when you forward to a level which is comparable to me, I will see you as a foe, or I will see you, I will actually see the effect, I should say that. So typically what happens is that you then we'll define another is the visual, this is called the VCE set. So we're going to talk about that in a little bit. There's a physical definition of which is just simply when VBE becomes 4. But even though it's 4, it doesn't really, I don't actually see the effect, therefore I don't care. So that's when you don't see it in your characteristic, therefore you can push it a little bit downwards to see the effect, okay? But it has other implications on beta and stuff, so it's not necessarily always valid. But for circuit analysis, we typically use the red line rather than the yellow line to define the region for circuit analysis. Okay? So what we're going to do, the more interesting part is then, as I said, if I have a circuit where rather than having just the DC bias, because we're doing amplification, so the idea is that you want to have your signal, which is the modulating component, being amplified. So to actually analyze that, we need to establish something called a small signal model, the same as the diode. So how do you generate a small signal model for NPN transistor? And I want to emphasize, this is only valid when you're inactive. There's no small signal model. You can do it. You can establish one, but that is not useful. So typically, the small signal model is only for NPN transistor inactive. I want to emphasize again. So I want to build a small signal model for NPN transistor and active for small signal analysis. That is to say that if you're doing small signal analysis on devices operating in saturation or reverse active, that doesn't really, it's not helpful. I'm just saying that. It's typically, if you're operating in different modes, typically you're doing DC analysis, you think about it in different modes. If you want to amplify the signal, you have to make sure that your device is inactive, meaning that you want to have a voltage control current source in order for that to happen. To have a bit best performance. Okay? So we're only going to introduce small signal model for NPN transit, BJT in active mode. So to think about, okay. So one of the key parameters or model in this case is that I want to describe also a 3-terminal device. So I have, remember I have a BJT. So I'm looking at 3-terminal. I'm looking at whether this small signal base current modulation, how does it affect collector current and emitter current, collector and emitter current. So I'm looking at the relationship between, if I'm modulating the voltage or modulating current, what is the relationship between these modulated current or modulated voltages. So as I said, typically the key parameter here is that you modulate VBE and you want to see what is the corresponding collector current as a function of VBE. So this is typically our voltage. Remember, we're trying to establish a voltage control current source. So even for small signal, you want a voltage control current source, current that modulated with voltage at the input terminal. So to establish that, we're just going to draw our model. So the key component you want to establish is still a voltage control current source. This will be C, B, E. So as with this large signal model, you first identify 3 terminals. And on this side, we're simply going to use a linearized component, which is typically referred to as transconductance. Let me redefine this. I'm not really using it. Okay. Let me not move too fast. Okay. So if you're looking at the large signal model on the right, your B is being defined by a diode. Therefore, I could use a diode small signal model, which is RD, right? On the right-hand side, and the voltage across here, which are used to establish my collector current. So what I need to do is now describing this would then allow me to describe the 3-terminal current. One is to describe the relationship between base current and collector current by having a diode transconductance. The transconductance referred to a scaled diode. And then this is called the transconductance. GM is referred to as, this is a very, very important, we're going to talk about what is the meaning of this transconductance. GM is one of the key parameters if you're doing a device design or you're a technology developer. What you need to deliver is, one of the key parameters is GM, transconductance. That what is transconductance is actually how many turns does it take for the water to change by how many fold. So this is the sensitivity of your transistor. So let's look at the definition of GM. So if you look at the equation, what it does is that transconductance wanted to describe whatever small little current change. So because this is a small signal model, so this is IC. This is the small signal change in IB. This is IE. So if you look at that equation, what it does is that GM BB, simply based on this model, is describing IC. So GM is defined as IC VBE. And because VBE is a small little change, therefore, if you want to use a DC levels, this is VBE. If you look at it in a large signal sense, that would be this, right? Coming from this model, you will get that. So let's see what it is. So IC, we'll go back to our exponential model. IC is IS exponential VBE over VT. So you simply insert that in, and we should be able to get IS over VT exponential VBE over VT. So you simply do the derivative and get this. And what is this? This is IC. Therefore, okay, so this is very similar to the diode equation. In diode, we use RD. This case, we're using IC, so transconductance. So transconductance in this case, so you can find your transconductance will be directly proportional to IS, inverse proportional to VT. Okay? So we already have what? Yes? Oh, yes, yes. Thank you. Thank you. Yep. Okay, so then we get the transconductance. Transconductance can be determined by the quiescent current. So IC would then stand for, rather than arbitrary IC, this would then, I want to make a correction, is that this is typically your operating point IC. So it's ICQ. Will be depending on where you're standing. This is the same as determine the diode. This is the same as this. So it actually, basically, what does this refer? If you look at this plot, let me get rid of the, let me just draw it here. So what does this refer? Physically, this is IC VBE. If I'm plotting this, it is exponentially increase. So I'm looking at this particular ICQ, which is my operating point. And at this particular point, if I'm changing this, this is my small signal changes and corresponding changes in current, will then refer to as that. So the slope itself in this plot, at this particular point, the slope at this particular point will then be Gn at this operating point. So ICQ refer to our operating point, biasing current point. So ICQ is at operating point, or because it's current, so this is typically being determined by the biasing current. To be more precise, is the DC biasing current level. You will find out in later okay, the DC biasing level will then determine your transconductance. Okay, good. So the other thing we need to establish, other than GM transconductance, that's one of the parameters. The other is RD. So remember, RD is to represent a diode's biasing condition, resistance. The diode resistance, as we already know, is VT divided by the currents passing through the diode. In this case, this equals to IB, right? So you can rewrite this as this. The diode current is, in this case, because we're only taking the whole part, therefore it's 1 over beta times the collector current. So this will be 1 over beta IC. Let me rewrite this. So RD by definition is VT IDQ. In this case, because we're only taking the whole current part, so this is the same as the base current, VT. I'm adding a Q just to emphasize this in operating point. So this will be this. Therefore, if you look at this, let me rearrange this. So if I'm putting beta on top, this will be ICQ divided by VT. Okay? This is the same, right? So what is this? Correct. So your RD will then become beta GM. The reason why we're using this is that it will make your life easier because you start with ICQ, getting GM, and then you can get all the parameters. So the final model will be somewhat refined in its notation. So the small signal BJT, the BJT small signal model will look something like this. You simply have a current control, voltage control current source controlled by the voltage across this terminal. So let me highlight the terminal. This is your base emitter collector. I have two key parameters instead of having VBE. This is more like the conventional thing. Because this structure looks like a pie, therefore, typically we refer this as the voltage between this is called V pi. This is just a convention. And this is called R pi. The resistance is called R pi. Therefore, your current will be GM V pi. Your collector current will be GM V pi. So V pi will stand for VBE. V pi is simply a substitute for VBE, small signal VBE. Okay? So this is just a convention. So as I said, two key parameters in this small signal model. There's supposed to be three. We're going to talk about that a little bit. We're going to add more complicated model. But first order model, meaning that you're only looking at the big picture, which is you look at collector current controlled by transconductance and then R pi. Two key parameters. How does one come to these two key parameters? You start with, so the procedure is that we start with finding out where your DC biasing point is, and then we can find GM, which is ICQ divided by VT, and then you can conclude, you can find out R pi, which is beta. That's the procedure. So you start with finding out where your DC bias point is, and then come down to finding out the most important parameter in small signal control, which is transconductance, meaning that when I modulate my input, how much the current changes at the output terminal. And then, of course, we analyze how the input current changes as well. Okay? So once we're equipped with the tools of doing small signal analysis device, as I said, very limited, is on a BJT device on small signal model. Even though it's very limited, I'm just going to tell you that for the next, this is chapter 4. When I talk about chapter 5, most of your circuit on chapter 5 is supposed to be valid in that mode. Otherwise, your design is a failure. So you want to make sure that you're actually placing your singer to this to the appropriate point on the stage. So this is the same thing we're talking about. So once we, as I said, once we equip with the small signal analysis tools, We're just going to go through an example so you get a sense as to why are we going through all the trouble of establishing these models, and how, what can this understanding, or what does this transistor allow us to achieve in terms of signal processing, especially analog signal processing. So let's going through a example again. Suppose it is the third example. I don't know. I didn't get a number. So let's use the same, very similar architecture. I'm going to use the reason why we're using this architecture a lot is because that it's the most effective in amplifying signal. A small signal. So let's say this is VCC, and I'm having a collector bias of 100 ohm. And instead of having a DC bias, I would then have a small signal input, and then establish another bias here. This is 0.8 volt. Okay? So this is generally referred to as a common emitter. This is your V out. Okay? So this is generally referred to as a common emitter amplifier. As I said, the reason why it's called common emitter, I'm going to explain that in chapter 5, because there's different common. You can count on emitter, base, or collector, right? There's basically 3 terminals to common. So because it's a 3-terminal device, the way to think about this is that common means that it's the reference. Therefore, your signal is going through in from here, out from there. So these are not common mode because it fluctuates. So common means it's the general reference. Okay? So it's typically connected to ground or other DC bias. It's fine. As long as it's not carrying signal, the terminal is referred to as common. Okay? So the reason why it's called CE stage, let me spread it out, it's called a common emitter stage. Okay? Sometimes referred as to a stage because an amplifier typically have multiple stages for different, to achieve different purposes. So let's come back to the circuit. So as I said, this is my input signal. I want to look at what my output signal changes in correspond to an input signal. So what we want, first of all, I'm going to give you these parameters. A complete process Q1. So there's basically, this is 1.8 volt. Okay? So there's 3 parts of the problem. First, before we do any small signal analysis, you wanted to establish your small signal equivalent model. And also with parameters, with GM, R pi. These are the 2 describing your 3-terminal relationship, current relationship. And then, if I'm assuming my Vs equals to V1 sine omega t, I'll ask you to find out how IC modulate with time. And in here, we're assuming that signal is very small, it's 1 million. You're carrying a very small input signal with 1 millivolt. What is the corresponding input? And how much does it amplify? So the last thing is ask you to find V out. As I said, because this is the small, lower case, capital case. Therefore, it contains DC and AC. So this is the DC part. This is the AC part. This will then correspond to your your input signal. Okay? So once we establish that, you should be able to follow up with the analysis to get the final answer. So what is the first step? I forgot to give you device parameters, sorry. So the part missing is, of course, we need to describe the transistor we picked. So to describe this, because I'm giving you a bias, therefore, IS should give you an IS, right? And then, of course, beta. So this, we're using exponential model to start. So what is the first step? What do you think? And to build our small signal equivalent model, what do we need? What? Excuse me. Well, we need ICQ, right? You start with ICQ. So how do you start with ICQ? Exponential model, right? So exponential model already tell us that. So when you're doing this DC analysis, you can simply skip this. Therefore, where ICQ stands for IS exponential VBE VT. And here, VBE is 0.8 volt. And we already know this number, so we should be able to find out that this is about 6.9 milliamp. So you simply insert your bias level, and we should be able to find out our ICQ, right? Once we have the ICQ, then you should be able to construct the small signal model. So part B, this is still part A, sorry. So our small signal model will look something like this. Remember, I have my base. So this is GM. So in this, we need to find out two of the parameters that we need to build our small signal model. So GM will simply be ICQ divided by VT. And this is about 0.27 amp per volt. Okay? And then simply R pi will be beta GM. We're just going to follow the equation, and then this will give us about 380 ohms. So once we have these two parameters, we can use that into our model. So that's our model and these parameters. So the next step is then, is a little bit challenging, but I want to set up the ground rule. We're going to do that, do a lot of these analysis in the following in the following study when we start to introduce the idea of amplification. But first of all, once I have this model, how do I insert and combine it? Remember, this is the base, collector, and emitter. So aside from having this model, remember we have to establish a small signal equivalent circuit. So this is the model you insert into the circuit. So what is the corresponding circuit? Remember the emitter in this small signal equivalent circuit. So if I want to insert that into, so the second part for the analysis, we want to establish the, we call it small signal. The equivalent model is used inside the equivalent circuits, right? So you want to, so what is the equivalent circuit? In a small signal equivalent circuit, you assume all DC level as ground. So let me give the guideline. So if we're analyzing small signal, we're assuming that all DC sources AC ground. Okay, so this is very important. How does we connect this into that circuit, link to that circuit? So if you look at the collector, the collector is connected to RC, and this terminal will then deliver my output signal, only the small signal part, right? This is RC. And what's the other side of RC, which is VCC, right? If you look at this terminal, the collector is connected to this and connected to ground, correct? But this is not the real ground. This is typically referred to as AC ground. If you look at the circuit, it's VCC, but for AC signal, it's a ground because it doesn't move with time. So this is referred to AC ground. And your emitter is really ground, so it doesn't really, it's real ground because my emitter is ground. And then if I look at on the left-hand side, I'm using the green to establish the circuit. So on the left-hand side, I would then have my source and then connected to VBE. So this is another AC ground. This is a DC level, so this is AC ground. Let me highlight, this is VBE because this is DC level. This is VCC. Even though it's VCC, but we view it as an AC ground. So you see ground, ground, ground. So there you get your equivalent circuit. Once we have this equivalent circuit, then we can proceed to finding out what is the corresponding output characteristic. So if you look at the output characteristic, VL, will then be the current at the output terminal, which is I.O. Let's define it as I.O. times RC. So what is I.O.? If you look at this terminal, I.O. plus this current equals to 0. So I.O. is minus GM V pi RC. So we look at what V pi. What is V pi? V pi is voltage across. So V pi equals to Vs. Therefore, is minus GM RC Vs. So you actually get a voltage gain. If you look at the voltage gain, output voltage against input signal is minus GMRC. This is our small signal. I'm moving a little fast, so we're already coming to part C, because this is what you get. Your output and input relationship would then be amplified by a factor of GM RC, right? So what is GM? So let's find out the gain. How much gain do we get? If you look at the absolute value of the gain is GMRC. And here our GM is 0.27. My RC is 100. So I'm having a gain of 27 volt to volt. Okay? This is to say my output voltage. If I want to write down my output voltage, I'm just going to use this. Your output voltage here, this will simply be minus 27 times 1 millivolt sine omega t. So it will be minus 27 millivolt sine omega t. Okay? I want to keep the minus sign to show you that the minus sign simply refers to that there's a phase shift of 180 degrees in terms of your signal. So if I'm drawing the signal, let me draw the signal first. So part B, you can do it on your own. It's very simple. from this directly move to RC. So you have a voltage gain, as I said, about 27 volt to volt. So what it means is that if I'm drawing my input and output in a time scale, so remember my input terminal is at 0.8 volt, right? And then it modulates at a rate of 1 millivolt. So this is referred to as, I'm amplifying a little bit, 1 millivolt. Yeah. Okay. And then what is your output? If I ask you to plot it on the same plot, it will be biased at a higher voltage. I didn't actually find this. We need to find this, of course, Vout. What is your DC level at this terminal? So Vout, let me write it down. Vout is a DC component, so that would be VCC minus ICQ times RC. We already know our ICQ, so we should be simply insert that into, it will be 1.1 volt. So you will be adding 1.1 volt. This will also verify that Q1 is inactive. Right? So once we know that it's actually biasing at a high level. This will be centered at about 1.1 volts. And I want to emphasize that other than the amplification, meaning the magnitude of the signal will be 27 millivolts being amplified, and also inverting, meaning that it goes to the inverse direction. When input's up, it goes down. When input's down, it goes up. Make sure that I got it. So it's in the inverse direction. I'm not plotting it well, but just to give you a sense that it's inverting. When it's at its peak, it would at its lowest because of the minus sign. So you're having again, let me redraw this to be better fit. I'm in trouble plotting. So the blue will be the overall response. So that will be my V out. Also, both the DC and the AC. This will be the V in, which is VPE plus a small signal. Okay? So you get an inverting. I want to emphasize once again, the amplitude of this signal will be 27 millivolts. And then it will be inverting itself. And this is simply because of the structure of the device, because you're increase the current, therefore lowering the output voltage. Okay? Good? Any questions? We still have a little time on, did I miss? Oh, IC. I didn't get the IC. I should say this. IC is fairly straightforward, it's this, right? So IC, here, let me just write it down here. So IC will simply be, your small signal IC will simply be GM V pi. And we know that V pi is Vs. So you simply insert the number, and then we get it to be 0.266, 0.27. Milliamp. This is just to show you that by modulating collector current, this is how much does one modulate the collector current, and it will then be reflected on its output voltage. Okay? Good? Okay, I think it's a good time to wrap up today's discussion. And I want to remind you that we'll be posting the first homework probably end of this week. So just keep an eye on having to deliver homework 1. It will be mostly simulation problems, okay?